let's look at how we'd actually write a program and how a program would actually get executed. So I've written a program here that basically says load A 14. And so what that's saying is load the contents of memory address 14 into the A register. And then it's saying add 15. And what that means is add the contents of memory location 15 to the A register and put the result in the A register. And then the last instruction is out. And what that instruction means is take the contents of the A register and output it to the display. Now you might be wondering, where do these commands come from? How do we, why does load A 14 mean that? And this is actually a really cool thing, is we're building this computer ourselves, and so we get to define what the language is. We get to define what these commands are. So I made these up. And really, we can come up with any commands that we want, as long as it's some operation that we can actually do with this computer. And we can call them whatever we want, and we can come up with whatever we want. So this is just what I've come up with, is this load A command, and I've decided that what that means is it means to take whatever's in the location that's referred to in memory and put it into the A register. And then I've decided that this add command, what it means is take whatever's in this location and add it to the A register and leave the contents in the A register. And then the output command, of course, just means take whatever's in the A register and output it. And so we could come up with whatever commands we want. If we wanted to subtract, we could do that. The computer knows how to subtract. If we want to move things into the B register, we could have a command that does that. Anything that we can do with this computer, we can make a command to do that. So then how do we actually program these things into the computer? So for that, we want to put these instructions in memory, because the computer is going to execute programs from memory. And again, we're making the computer. We can make whatever choices we want to make here, but what I think makes sense is for the first instruction to go at memory location 0, and then the next instruction to go in location 1, and then the last instruction here to go in location 2. That seems to make the most sense. Just start at 0, 1, 2. So the memory locations for these are going to be 0, 0, 0, 0, 0, 0, 0, 1, and 0, 0, 1, 0. So that's where in memory these commands are going to go. But how do we actually put this command load A14 into memory location 0? Because load A that's not a, this is an 8-bit value. Load LDA or load A is sort of a mnemonic word. And so again, since we're building the computer, we may get to make the decision here of what this actually is represented as in binary. So since we get to make up this command, we also get to make up what value it corresponds to. So I'm going to say LDA corresponds to 0001. That's LDA. And so that'll be the first 4 bits. And then the next 4 bits of the command are going to be the actual memory location that we're loading from. And so in this case, 14. And so 14 in binary is 1110. So this LDA 14 command, we're actually going to put it into memory as 00011110. And that corresponds to load A 14. And again, we're just making this up. I could have used any 4-bit value as long as I'm consistent with that value meaning load A. So same thing with add. Of course, I can't use 0001 for add. I've got to use something different. So I'll just use 0010. I'll just use 2. And so that'll be the binary representation of add. And then, of course, along with the add instruction, we've got to tell it what address to add the contents from. And so that's 15, which is just all ones. And then output. Again, this is a new command. We get to decide what the representation is. I could go with 3. Or I could go with anything I want. I could just go 1110, and I think that'll be what our output is. And in this case, output, I'm going to say this command says take whatever's in the A register and output it to the output display. And so I don't really need to tell it anything else here. So the other 4 bits could be anything that we choose. So we'll just set them all to 0. And you'll see when we actually build this output command in the logic here, we'll just ignore, we won't use those 4 bits for anything. So they could really be anything. But of course, you could imagine having a command that says like output from memory and then a memory address, and it would go fetch the contents of that memory and output it. You could very easily define a command, but we're not going to do that just yet. So this will be the program that we try to program in here. And so we can program it just by setting those values into memory. So what does that mean? So if we want to be in programming mode here, we go to address 0, and so we're at address 0, and we want to set this 0001 1110. So 0001 1110, and we'll program that in. And so now at address 0, we've got that command. So then we'll go to address 1 here, and then we'll put in this, so 0010 1111, and we'll program that. So now we have our second command in memory, and then we'll go to address 2, our last command, oops, and program in our output command. So that's just 1110, and then actually the rest don't matter, but I'll set them all to zeros and program that. And so there's our output command. So now we've actually programmed our computer. We've put the program in the computer. Of course, it's not going to work because we don't have any control logic yet, but we can start to step through and see how this might actually work once we build the control logic, so we'll get a sense of what the control logic needs to do. And of course, for this program to make sense, what we're saying is that we're loading the contents of memory location 14, and we're adding to it the contents of 15, and we're outputting that. So we need to put some data in address 14 and 15. So if I go to 14, it's got some data here. Let me put some other data. So if we just go here to address location 14, which is 1110, and 15, which is 1111, I'm going to put some data here. Let's say 0001110. And in this location, we'll say 00001110. And this, if we convert it to decimal, is 28, and this is 14. And so what this program's really going to do is it's going to say load whatever's in memory location 14, which is the number 28, into the A register, add whatever's in 15, so it's going to add 14 to that, and then it's going to output whatever the sum of those two numbers is. So we're at 14, so I'll program in the first number, and then we'll go to 15 and program in the next number. So we got 14 and 15. And if we go back to 0, we've got our first command there. And so I'll switch this back to program, so the memory address is no longer controlled by the dip switches, it's controlled by the memory address register. So now we've got this program programmed in here, and obviously it's not doing anything, but of course there's no control logic, so it wouldn't do anything. If we had the control logic built already, then the program would run. But that's obviously not happening. So we need to kind of step through this step by step, and I need to essentially manipulate these control lines to do what the control logic would do if it were built. And that way, that should help you understand what it is we're actually trying to do when we build the control logic. So to step through step by step, I'm going to stop the clock, and we can still step the clock manually by pushing this button. And so we're going to go super slow through this and go step by step. So the first thing that's going to happen when we start to execute a program, or really anytime we start to execute a command, is we need to load the command from memory and put it in the instruction register, because the instruction register is what tells us what command we're currently running. And so the beginning of executing any command is a fetch cycle, where we fetch the instruction from memory and put it into the instruction register. Now the other component that comes into play here is the program counter, which is up here, because the program counter is going to count through which instruction we're on. And it starts at 0, which is where it is right now. But once we execute the first instruction, it's going to go to 1 and then 2, and then it would keep going 3, 4, 5, and so forth until we stopped executing our program. So our program counter is at 0, which is where we want to start. And the first instruction that we want to fetch from memory is in memory location 0. But in order to get to memory location 0, of course, we're already there, but we're just sort of there by accident. Really, to get there, what we need to do is we need to take the program counter, the contents of the program counter, which is 0 in this case, but as we get to the next instruction, you'll see it's 1 or 2. We need to take the program counter and move that value into the memory address register here. So what we're going to do is we're going to say program counter out, so counter out, which is here, and then memory address register in, which is over here. So this is saying take the program counter and put its value onto the bus. And so there's a 0 on the bus. There's a 0 here. This is not going to look very interesting. There's a 0 in the program counter. There's now a 0 on the bus. And then we're going to take the 0 from the bus and put it into the memory address register. And so all of that's going to happen on the next clock pulse. So there's the clock pulse. And yeah, that 0 just went over there. I'm not sure if you saw it, but no, that 0 went over there. It'll be more interesting for the next instruction, trust me. So the first thing we did, so if we're executing this LDA, which is load A 14, that's the first instruction we're executing. And the first thing we did is we said program counter out and memory address register in. And then we pulsed the clock. So this is the first thing we did. The next thing we're going to do is we want to take the contents of memory. So now that this is pointing at 0, of course it was before, but just bear with me. This is now pointing at address 0. So what we're seeing here is the contents of address 0, which is this here, this 0001110, which is the load A14. So this is the load A14 command. We need to move that to the instruction register. And so to do that, what we want to do is turn all these things off. And so for the next clock cycle, we want to take the RAM out, which is this here. So RAM out, and you can see the contents of RAM is now on the bus. And then we want to say instruction register in, which is right here. So we're going to say instruction register in. And of course, nothing happens yet until the clock pulse, which is good because that gives us time to set up and change what's going on in the control logic here before the next clock pulse. The next clock pulse here, and there it goes from the RAM into the instruction register. And so you can see I actually use different color LEDs here. So the blue indicates the instruction. So LDA is load A, and so 0001 corresponds to that. So you can see that. And then the yellow is kind of the operand, the 14. So now that we've loaded the instruction, so the next thing we did here, right, was RAM out, and instruction register in. So this was the next set of signals that we did for the next clock pulse. And then the last thing we want to do as part of the fetch cycle is actually increment the program counter so that the next time through the program counter is pointing to the next instruction we want to load. So we'll turn off these signals. And now we just want the counter enable signal to be high or active. So counter enable is active. And so now in the next clock cycle, the program counter will increment. And so there it goes, it increments to 1. And so that's going to stay there in the program counter just to keep track of where we are in our program so that the next instruction we execute will be fetched from memory location 1. So now we can set that low. So that was counter enable, which increments the program counter. So these are the 3 steps we've done so far. We've moved the address from the program counter to the memory address register. We've loaded the instruction from RAM into the instruction register, and we've incremented the program counter. And we're going to do that for every instruction that we execute. So when we build the control logic, it's going to have to kind of know how to do this. Once we've done this, the next thing that we're going to do is actually execute the instruction. So now we've got the instruction. The control logic can look in the instruction register and see, okay, the instruction is 0001. What does that mean? Well, that means load A. And so the logic that we build here is going to have to take that into account and know what to do with load A. Well, we've decided that load A means take the contents of memory address, whatever this is 14 in this case, and put that memory into the A register. So the first thing we've got to do is actually get the memory address register pointing at 14. So to do that, we want to take the contents of the instruction register, or really just the lower 4 bits, which is actually the only part of the instruction register that's hooked up for output to the bus. So if we do instruction register out, if we enable that signal, you'll see only the lower 4 bits actually go out on the bus. The top 4 bits stay all zeros, and that's just because we've only hooked up those 4 signals. And so now what we can do is we can take those lower 4 bits and read that into the memory address register. So if we say memory address register in, so we've got instruction register out and memory address register in. Now, if we do that and then do a clock cycle, when that clock goes high, that address goes into the memory address register. And when that happens, we're now pointing our memory at location 14. And that's the value that we want to put into the A register. And so the next thing we'll do is take the contents of RAM, so we'll say RAM out, put that on the bus. So now that's on the bus, and we want to put that in the A register. So we're going to say RAM out and A register in. And so the A register in, we'll set that. And so now with that set, A in, on the next clock cycle, this value will go into the A register. And there it is. And with that, we have actually executed this load A 14 operation. So the opcode LDA, load A, and the operand 14, memory location 14. We have loaded the contents of memory location 14 into the A register. And we just had to follow this. And so when we build the when we actually build the logic that does this, instead of us fiddling around with the signals for each step, we'll build logic that knows what those signals are. And so with that, we can move on to the next instruction, which is add 15. Add 15 is the next instruction. And all of the instructions start the same way. They start with this fetch operation. Because when we build this logic, we're not going to know that the next instruction is an add 15. We've got to fetch it from memory so that we can look in the instruction register here to actually know what to do. So this first part is going to be the same. We're going to say counter out, memory address register in, and that's going to be 1 clock cycle. And then RAM out, instruction register in, and then counter enable to increment the counter. So this is the exact same, and it's going to be the exact same for every instruction. So let's actually do that and see what happens. So counter out, memory address register in. So let's get rid of these things. And we want to say counter out and memory address register in. And what this is going to do when we execute this clock cycle is it's going to take the contents of the program counter, which is 1. That's already being output on the bus. But then when the clock edge comes, that's going to be latched into the memory address register. And so we get a 1 there. And that's how we know that we're on to instruction 1, which is the add 15. We've gone from 0, now we're at 1. And so this is the instruction for the add 15. So the next thing we do is RAM out, instruction register in. So let's turn off these signals here. And we're going to say RAM out, which is this, and instruction register in, which is that. And so we see the contents of RAM is now on the bus, and with the next clock pulse, it goes to the instruction register. And so now, the instruction register has loaded this add 15 command. And then the last thing we do is counter enable, which just increments the program counter. So we'll turn off this stuff, and we'll say counter enable, which is that. And then 1 more clock cycle, and that'll increment the program counter up here. So that says next time through, we're going to be looking at instruction 2. But that's the fetch cycle. And so now what we do after this point, in this case, we did these commands that did the load A14. But in this case, now that we've fetched it, we can, or the logic that we're going to build can look at what's in the instruction register, and it can see well, there's a 0010 is the instruction. And 0010 is different than the last time around. So 0010 is now an add, it's not a load A. And so we're going to do something different. And so the different thing that we're going to do is we want to fetch whatever's in memory location 15 and add it to the A register. So the first thing we need to do is actually the same. We need to take the 15 that's in the instruction register and move that into the memory address register. So that's actually going to be the same, because we need to fetch something out of memory. So instruction register out and the memory address register in. And so this will take this 15 and put it in the memory address register. And there it is. And so now what we see in memory is this value that we put in location 15, which is the 14. And so this, we now want to basically add this to what the contents of the A register. So what we did last time is we said take whatever's in RAM and put it into the A register. We don't want to do that. We want to add it to the A register. So in order to add it, we need to put it over in the B register, which will then allow us to add what's currently in A with what's in B and get that out. So let's take what's in memory. So we're going to say RAM out. That'll be the first thing we do, or the first signal that we set. So RAM out is here, and we don't want to go in the memory address register. So RAM out, so we're putting this on the bus, and then we want to go into the B register. So B in. And so now, on the next clock cycle, this value will go into the B register. And there it is. And you see, when that goes in the B register, the ALU is constantly just adding these two values together. And so the sum of A plus B is sitting here in the ALU. And so we did RAM out, we did B in. Now the next thing we want to do is we want to get that sum into the A register. And again, that's just because we've decided the way we want the add instruction to work is we want it to load whatever's in that memory location that's referred to and add it to whatever's already in the A register and put the result in the A register. So now we need to do that last part. We need to put the result in the A register. So we're going to take the sum out, which is the EO. So we want to, let's first turn off these other signals. And so we're going to take the sum out, this EO signal. And so that's going to put the result out on the bus. And then we want to put that into the A register. So we want to say A in. And so we've got A in. And now in the next clock cycle, it'll latch this value into the A register. And this is why it's important that we're doing this on the rising edge of the clock, because when it latches into that A register, it'll also feed through into the sum register, and this will update. But we'll have already latched it just that once on the rising edge. So let's do that. And so now the sum is latched into the A register. And of course, this sum updates because it's now the new A plus B. But we don't care about that. So we did the sum out, A in. And now we're done with this command. And so the last command is the output. And so again, we're going to start this command like every other, because if we're just this control logic down here, we don't know what the next command is. We've got to fetch it first. So we're going to do this counter out, memory address register in, RAM out, instruction register in, and then counter enable to increment the counter. So we always do these 3 steps first. So let's do that and see what happens. So counter out and memory address register in. And the counter is pointing at 2. So that should put a 2 in the memory address register, and it does. And so now if we look at what's in memory there, we see the next command that we're going to execute. So we're moving on. Our next thing we're going to do is RAM out instruction register in. We want to move this into the instruction register. Turn off these signals, and we want to say RAM out instruction register in. So we got RAM out instruction register in. That should move this into the instruction register, and it does. And now the next thing is just this counter enable to increment the counter. It isn't really necessary because we're going to stop at this point, but our control logic's always going to do this anyway. So this now increments that counter. So it says the next instruction we're going to execute is at location 3. And of course, we didn't put anything at 3, so we have no idea what that's going to do. But that's fine because I'm not going to keep going. And so now we've done these 3 steps to fetch. And the next thing we want to do is look at what is in the instruction register. And so we have a 1110. And again, what we do next depends on this. And 1110, we're going to say corresponds to this output command. And again, we get to make up what these things are. We're building the computer. So output, we're going to say that particular opcode means take what's in the A register and put it into the output register, which will show up then on the display. So that one's actually pretty easy. We just say A out and output register in. So let's give that a try. So we'll say A out. And you see when I enable that, you see the contents of the A register is now on the bus. And output register in, which is over here. Then on the next clock cycle, the contents of the bus should go into the output register and we should see the result there. So let's do that. And that didn't work at all. What happened? Output register in, do something. Well, of course, it would be the very last step that something doesn't work. So let's see here. We definitely have the value going out on the bus. So we've got our A out, that's working right. Make sure this is lined up right. So output register in is high. And if I look in here, it looks like that is in fact going up to here, which is the output register in signal. So that should be coming in from the bus. The clock is coming in here. We're ANDing the clock with that signal. So then the clock pulse should only pass through to the register here if this is active, and it is. So that clock pulse should latch in the contents of the bus in here and display it here. So why isn't that working? Well, let's start measuring stuff. So I'm going to hook my ground up here, and let's see. So output enable, that's this signal here. That is high. Let me actually stick something under there so this doesn't have as much glare. That's a little bit better. The glare, Okay, so that is fine. And then of course the clock input here is low, but then when we pulse the clock, it goes high-ish. Let's see, the output here is low, and that goes solidly high. So this should be going high. So this is the 74LS273 register. Let's just see what else. Got power going to here. This is reset. Do I have reset 74LS273? Aha, here we go. I just got the data sheet for the 74LS273, and the master reset is active low, and looks like it is tied low. So somehow maybe this popped out and I stuck it in the wrong place, but I bet that's the problem. This is active low, and it's constantly resetting this, which is why it's always 0. So let's set that high, that reset, and I bet that'll fix our problem here. So let's get this all out of the way. So now that we're not constantly resetting this, we've got our A register. Nope, wait a minute. That's not lined up. There we, oh yeah, okay. A register out and output register in. Okay, so the A register is out on the bus, output register in, and we're not constantly resetting it. So on the next clock pulse, that should read in the A register. And there it goes, 42, which is 28 plus 14 is our answer. And so that's basically how a program gets executed. And so what you can see is that we have a lot of freedom in what commands we create, because we get to define what the commands are. We get to call them whatever we want. We get to associate whatever binary equivalent for the opcode that we want, and we get to kind of define what operations we want that command to perform. But of course, we were stepping through this manually, but hopefully you can start to see that, with a little bit of logic, we could build something that does this, that sequences through these things automatically, because it's really just looking at, just kind of cycling through a set of commands, and it always starts with the same commands, and then when it gets to the point where it has to do something different based on which opcode we have here, it's able to look at what's in the instruction register. So hopefully this is starting to make sense. In the next video, we'll go a little bit deeper, and we'll actually start to build some components of the control logic.